Horizontal asymptotes. All right, we had a little activity a couple weeks ago. Y'all may remember when we got on Desmos and we tried all of the different dividings and we tried to make observations, and it went about as well as the maiden voyage of the Titanic. All right, we've learned about vertical asymptotes. Can y'all, any of you three, remind me about when we're going to have a vertical asymptote? Very good. Yes. So you're adding this to your notes. Review. Vertical asymptotes occur when the denominator is equal to 0. This is because why? Why can't we have the denominator equal to 0? It's one of the very big ideals from this unit. Say it one more time. Trinity on fire. This is because we cannot divide by 0. This is one of the biggest ideals in math. Division by 0 is undefined. Let's go. Underline and bold. Gosh, that's important. Okay. All right. Smaller note, if, control, underline, if we have a factor in both the numerator and denominator, that is the same, the associated 0 will produce a whole instead of a vertical asymptote. Okay, so that's a little review. Now we're going to put your pencil down when you're ready. From the beginning of my HRW, I need to select Algebra 2, that's our class. You will click on Student Resources. Then you will select Unit 4. Then you will select Module 9, Rational Functions. Then you will select 9.3, Graphing More Complicated Rational Functions. And then Student Addition Lesson 9.3. And then you will scroll on down to page 497. This box, I guarantee you a question on the test. So you might find a way to make a condensed version of this for your note card. All right. This box will go in your notes here. Control V. All right. I'm not going to leave that up. I'm going to just close your computers and I'm going to discuss it here briefly. All right. First of all, it references the degree of P of X and the degree of Q of X. What they mean here is that P of X is the numerator function, the top, and Q of X is the denominator function, the bottom. You can pause the video at this time and enter all these notes in your notebook. That's all the notes that there will be. The rest of the video explains the 3 conditions on the table. Okay, that makes sense. If the bottom is outgrowing the top, we would have a situation where it's approaching the x-axis. I'm going to quickly show some Desmos of that. Well, we just go to that what we were looking at the other day. I think we can pull that up. I'm reviewing the this was the document we looked at the other day. Okay, and it's saying if the bottom function has a higher degree than the top, the denominator function has a higher degree than the numerator. So I'm looking now at this little doc here. So Caroline, you pick me one where the bottom is a higher degree than the top. Can you see those okay? We want the bottom to be higher than what divided by what would give us that? By the bottom and the top, I mean the numerator and the denominator, okay? I want a function in the top that is a lower degree than the bottom. We want to make the denominator a higher degree. Are y'all with me? So you're just selecting something divided by something. About something, you're calling out those numbers. You know, like F1 divided by F2, whatever it might be. F12 divided by F7. That's not going to get it done. What is the degree of F12, Austin? When I say the degree of this polynomial, first of all, this is a trinomial, and we would say it's a quadratic trinomial. When I say, what is the degree of F5? What do I mean? It's a second degree. How did you come up with that, Caroline? Good. The degree of the polynomial is the highest exponent. That's it. Okay? All right. So, Austin, what would be the degree of function 7? It would be 1. Does everybody see the implied 1 there with that x? Okay, so Caroline said F7 divided by F12. Trinity, what do you notice about F7 and F12? They both have a degree of 1. So this will be a case we're going to examine when the degree is the same. Okay, but I want the degree of the numerator to be less than the degree of the denominator. I want the bottom bigger. Try again, Caroline. Good. F9 is degree what? Good. F8 is degree? All right. This is an example that we want to look at. So I'm coming back to my business here. I want to do 9. Noting A is the top and B is the bottom. We want to do 9 divided by 8, right? 9 divided by 8. And what we're looking to observe here are what are called the horizontal asymptotes. It's the line the graph approaches as we move out there. Not in the middle, but at the infinities. And here, I'm going to graph now. Well, I don't have to graph it. It's the x-axis. It's already graphed. Can y'all see that these two black curves are flattening out on the x-axis as we go to the infinities? And if I zoom out, you can see it a little better. Can y'all see the lines are flattening out on the x-axis? Okay, that's the horizontal asymptote. It is the x-axis. The x-axis is the line y equals 0. Okay? That's the name. All right. So that's this first case. When the degree of the top, the numerator, is less than the degree of the denominator. Now, second case, the degree of P of x is equal to the degree of Q of x. We're going to have A divided by B. What is the A divided by B? Well, we need to add another note here. Okay. In the top. Space, get out of there. Get out of there. For the table below, f of x is equal to p of x divided by q of x, and a is the leading coefficient of p, and b is the leading coefficient and A, comma B are leading coefficients. That is, A is the leading coefficient of P of x and B is the leading coefficient of Q of x. What do I mean by leading coefficient? Back to this little deal here. Trinity F9. Function 9. What is the leading coefficient there? It is The leading coefficient is 3. What makes it the leading coefficient? True, but I need a little more specific. Caroline, can you try to tighten up that? What makes 3 the leading coefficient of function 9? That's it. It is the coefficient of the largest power. Okay? Are y'all with me? All right. It doesn't matter about the order, although all these are ordered in decreasing power. The leading coefficient is the coefficient of the term with the largest exponent. Okay? So, Austin, what would be the leading coefficient of F10 here, function 10? Good. Trinity, what would be the leading coefficient of F11? Good. Y'all see the implied one there on number 11? Okay. So, if degree of P of X is the same as the degree of Q of X, the horizontal asymptote will go to A divided by B. That is a fraction of those leading coefficients. We're going to take a look at that real quick. I'm going to tell you which one we're going to look at. I'm going to look at 9 divided by 10. First of all, on 9 and 10, do you see that the degree is the same in 9 and 10? Okay, so our horizontal asymptote is going to go towards the fraction that is the leading coefficient. So in this case, that would be 3 over 2. And 3 over 2 is 1.5. The reason that is because when you put really big numbers in here for x squared, the x squared is going to dominate the function. And it's basically like the x squared is going to cancel with the x squared to just leave the 3 over 2. All right? So here we go. I'm looking back here. I'm going to do, what did I just say? 3 over, no. Which functions was I dividing? 9 divided by 10. 9, we already got 9. That's convenient. Here comes 10. All right. This time, you can kind of see that it's not the x-axis anymore. What it is it's the line y equals 3 over 2. And I'm going to type that in. Y equals 3 divided by 2. Y'all see the red line? And y'all can see how the graph is. It looks like over here, y'all, that it's touching it. It's just a resolution deal. It's actually not touching it. It's flattening out there. Can you see how they're flattening out at the line 3 over 2? Okay. All right. Lastly, the last note here, horizontal asymptote. If the top is bigger than the bottom, there is no horizontal asymptote. The function instead increases or decreases without bound. If the top is growing bigger than the bottom, it's just going to go off to infinity. And that makes sense too. I'll quickly show one of those. Pick me one where the top is bigger than the bottom. Say it again. I want the degree of the numerator greater than the degree of the denominator. 14 and 13, what are their degrees? What are the degrees of 14 and 13? So they're the same, aren't they? So this horizontal asymptote, if I did 14 divided by 13, what would it be? If it was 13 divided by 14, it would be 1/4. Good. If it were 14 divided by 13, it would be 4 over 1, or 4. That's not bad. Go again, Austin. 14 divided by 12. 14 divided by 12 is x squared over x. So that's going to get big without bound. We'll look at that. 14 over 12. 14 over, nope, I got it wrong. I want that to be 14 and that to be 12. All right, here you can see, and I will kill that one. The graph, there is no horizontal asymptote. It's not flattening out. It's getting big without bound. And what we would see here is what's called a slant asymptote. You can imagine like a diagonal line that it's going through. We won't be tested on slant asymptotes. We did mention it, but it won't appear on the test. Okay. There's a slant asymptote here, and it would occur at 4. for X, I mean to say. All right. Any questions about that? Okay. So for you should include this entire graphic here in your notes, except for this last box. You want to key on the fact that there is no horizontal asymptote. If you included this on your your note page, your card note page, I would just have that last line here. That'll really shorten it up. Go ahead and write this entire box in your notes. These are required notes. Include this entire box, but highlight there is no horizontal asymptote. If you were putting this on your card for the test, I would simply put there is no horizontal asymptote instead of that entire information. But this entire box, everything you see here is required notes. That is all.